Hello, today we're going to be putting together some transistor circuits and making power amplifiers. Power amplifiers are generally large signal amplifiers, and they usually deal in the watts, 1 watt or higher. Although there are power amplifiers that operate at lower power ratings than that. Generally speaking, a power amplifier is something that you need to be careful of heat dissipation. You need to heat sink it or provide good airflow and things like that. These are linear amplifiers that we're going to be talking about. There are nonlinear amplifiers or switching type amplifiers that we get into later on. But this chapter has to do strictly with linear amplifiers, meaning that you have a linear relationship between the output voltage and the input voltage, and all through the signal chain are representations of that input voltage or input waveform. Switching amplifiers don't work that way, but they're much more efficient. But again, we'll get into that later. Okay. So in this case, we have an amplifier that has an inverted a transfer function, so the input rises and the output falls. And this would be something that would be typical of a common emitter amplifier that we talked about last time. A common collector amplifier, however, emitter follower, you would not have this inversion happening, remember. It's a voltage follower. We'll look at both topologies in this chapter as well. See if I get my slides working here. So we could draw the load line. Again, we get back to this load line. There's a DC load line, an AC load line. The DC load line is something we'll focus on here. The Q point, quiescent point, is when there's no signal. It's not really amplifying anything. It's just sitting there with 0 volts on the input, silence, if you will. And Class A amplifier is the least efficient. Okay, and part of the reason is that it's on all the time. Notice that there's a current going through the collector circuit, and there's a voltage across the collector emitter circuit here, sitting right here. So what's the power being dissipated in this transistor right now at Q? Well, it's ICQ times VCEQ. And if you have a 15 volt cutoff voltage here, DC cutoff voltage, right? And let's say this is about halfway down. That's 7.5 volts times whatever current you have to supply in order to support that 7.5 volts through the load. And we'll look at a schematic here in a moment. Yeah, so this is the power dissipated is ICQ times VCEQ. I wanted to mention something. We have an exam in a couple of weeks, the beginning of November. You might want to start putting together a formula sheet. In other words, just an 8.5 by 11 sheet of paper. Now, when I have face-to-face classes, it seems like a long time ago now, I was allowed everybody to use a formula sheet during the exam. And I encouraged everybody to take that formula sheet that you create at the very beginning of a series of lectures or lessons and use that to do your homework and use it to do the examples in the textbook. And so when you take that to the exam, you kind of know where to go, where to look on the formula sheet to find the corresponding formula to use to solve the problem. So here's one. Right here, ICQ times VCEQ is the quiescent power. So you might want to put that one down on your formula sheet. There's a section in the back of the textbook that has all the relevant formulas for that particular chapter. Actually, in the back of each chapter in the textbook, I should say. That's a good place to start. But what's most important is that you need to use that formula sheet during your homework, during your studies, before you get to the exam, because if you just make it up like the night before the exam, you won't know where to look. You won't know what the formulas are for. It's pretty much useless. So I encourage everybody to do that. It can be a real help in getting through an exam quickly. And there'll be several formulas during this presentation here, I think. Okay, so power gain is basically the output power divided by the input power. It can't be greater than a half ICQ VCEQ, particularly for a Class A amplifier, right? Because you're sitting right in the middle of the load line. And they're really lousy when it comes to efficiency, Class A's, because they're always turning and burning. They're sitting, even when there's no signal, they're dissipating power. So they're pretty crummy when it comes to that. Here's a Class A power amplifier. This is in a, what topology is this? This looks like kind of like a Darlington setup, and it's a, emitter follower, because the signal comes off of the emitter. So that's how you know that, right? And you also know that emitter followers generally have a voltage gain of about 1. Okay, so in this case, there's a 3-volt peak-to-peak signal coming in here. You're probably going to get about a 3-volt peak-to-peak signal coming on the output. Now, is there power gain associated with that? Yeah, because there's extra current now available through this Darlington arrangement. Okay, so there is power gain. So this common collector, again, emitter follower, same thing, just different name for each one. I mean, two different names for the same circuit. So the output is about 3 volts, peak to peak. Power delivered to the speaker is that 3 volts RMS. Remember, power is always an RMS. So here's another good formula for you to put on your formula sheet. This 1.06 is the equivalent RMS voltage of 3 volts peak to peak. Specifically, it's V peak times 0.707. So this is going to be, this 1.06 is 1.5 volts, which is half of that, right? Because V peak is half of V peak to peak. So it's 1.5 volts times 0.707. That's where that 1.06 comes from. So it's 1.06 volts RMS squared divided by 8, V squared over R. And let's see, we get 140 milliwatts. Okay, that's enough to power a little speaker. You could hook a little microphone up to that, or maybe not a microphone, maybe a line level output from your iPhone or your stereo or something, and that would power the speaker. Good little circuit here. You can get this common collector, common collector circuit, Darlington circuit in one chip. I think LM385 is basically this little speaker amplifier for you hobbyists. Here's another little example, a little follow-up. If you have this Darlington, if they say it's 10,000 for the combined beta, the total input resistance, which we went over during the last lecture, is the 2 input resistor, the 2 bias resistors in parallel times beta times the parallel resistance of the emitter resistor and the load resistor. Remember, these are in parallel essentially under AC conditions, particularly because this capacitor shorts out. And then you have to put beta in here because basically the increase in current results in a scaling of the input resistance as seen here through the transistors. To look at the emitter, looking at the emitter and load resistor, you have to scale it by beta. So that results in a total input resistance of 6.15K. And again, we do the V squared over R on that, and you get about 0.183 milliwatts on the input. With the output power, you can go ahead and just do that division if you want, and you get this answer, about 750 is what I got. With this formula, you can do, this is another formula you can put on your formula sheet. The power gain is the voltage gain squared times the input resistance divided by the load resistance. So they do this calculation here and get 769. And again, that's very close to the 140 milliwatts, which we got last time, divided by 0.183 milliwatts, and that's the power gain when you do that calculation. It's a little, comes in to be a little bit less. And it has to do with the fact that this is an exactly gain of 1 voltage gain. And multi-sim, you see it's about 1, a little higher on the red, you know. See, so you don't have quite a gain of 1 here, a little less. Okay, so that's with just one transistor. You put 2 transistors in there, okay, and then you get what's called a push-pull operation. And this is a transformer coupled push-pull amplifier. So it's pretty cool. It's very clever. As the waveform climbs here, it turns on Q1. As it falls, it turns on Q2. So they both work in tandem, okay? Q1 handles the positive part of the cycle. Q2 handles the negative part of the cycle. During the negative part of the cycle, Q1 is completely shut off. During the positive part of the cycle, Q2 is completely shut off. So in other words, when there is no signal sitting at 0, both transistors are shut off. Well, that's great, because if they're both shut off, they're both in cutoff, there's no current flowing through them, they're not getting hot. They're sitting there. So this is much more efficient than a Class A. Now, there is a problem with this. This is called Class B operation. The problem with this Class B is that how many volts do you need to have on either Q1 or Q2 in order to turn the transistor on before it starts dancing to begin with? Remember? Well, you have to overcome this VBE. How much is that? 0.7 volts. So this input voltage has to climb to 0.7 volts before Q1 starts to conduct. Or it has to fall to minus 0.7 volts before Q2 starts to conduct. Well, that results in a dead zone at in the very beginning, or the very middle of the output waveform. So if you look at this output waveform, you'll see this little step right here, okay? And that's called crossover distortion. All right, so Class B operation on the exam, if there's a fill in the blank, you say Class B amplifiers have blank distortion. You got to put crossover in there, okay? Because that's what's the problem with Class B. So what we have to do is we have to modify the circuit slightly, okay? And we put a center tap in this transformer to bias it up by 1 diode, okay? So this lifts up this point to 1 diode, which makes these transistors almost turn on. They're just sitting now ready to rock and roll, so that even the slightest little voltage that comes in on the input causes them to conduct. Now, the other important thing about this circuit is that, you know, all transistors aren't created equal, even if they're the same part number, all right? So this could be a 3904, this could be a 3904 or whatever, and that could be a 1N914 diode. Well, these 3 diodes, they all have maybe 0.7 volts, but maybe not. Maybe one's 0.69, maybe one's 0.71. So they're all different. So typically when you have a circuit like this, you use matched components. And in fact, in a Class AB, this is called Class AB operation, when they're biased up like this and almost turned on. These are all matched silicon on the same substrate. So basically cut out of the same piece of silicon. So they match. This fixes the crossover distortion problem, the Class AB circuit. You don't need a transformer to do this. You can do it, yeah, they're both NPN types on this circuit. You can do a circuit that uses complementary symmetry, uses an NPN and a PNP. It's still a push-pull Class AB operation, but the circuit looks like this. And what happens is this diode here, D1, is biased, is turned on, okay, and produces a 0.7 volt voltage right here. And then D2 is the same thing, and it produces a minus 0.7 volt bias right here. So this Q2 is just barely turned on. Again, these diodes and transistors are usually packaged in one integrated circuit, and they're all matched so that their forward voltage drop on the VBE and the diodes is identical. It's the only way you can do that. You can't have separate components because you don't know, what they're made on or what factory they came from and so on. So that's the only way to really do this correctly. Otherwise, you still get some crossover distortion. And this is a lot more typical, honestly, for a Class AB amplifier. And we use these at work to drive audio lines long distances. We put a little snubber out here, a little inductor and resistor combination. But this is a real common, nice circuit. It's very low distortion. It produces an AC waveform that is very, very close to the input waveform. And it's very linear. So that's a good amplifier right here, this Class AB complementary symmetry amplifier. And this down here just talks about what I was talking about. Each transistor, again, conducts for half the input cycle. When there is no signal, these transistors are shut off, so they're not dissipating any power. So that's good. What's the advantage of Class AB over B operation? No crossover distortion. They're both efficient, but Class AB doesn't have any crossover distortion, or has less crossover. In practical practice, it has less crossover distortion. Nothing's perfect, so it'll still have a little bit. So here's the AC load line of one of the transistors, okay, the NPN, okay, so that's the positive half. And the Q point is sitting way down here. So very low ICQ, ideally nothing, but there's always a little bit. And then here's VCE. So it's a very small power dissipation when it's in quiescent operation. And IC sat, of course, is the VCC divided by RL. That didn't change. It's whenever the transistor's totally turned on, completely saturated, okay, you're going to get IC divided by the load resistor. I'm sorry, VCC divided by the load resistor for the current. So we can draw the AC load line for the NPN transistor. This sounds scary, but it's not. I mean, think about it. When the transistor's totally turned on, this is a short across the collector emitter. So you get a current, which is 15 volts divided by 30, this load resistor. But that's a half an amp, right? The other end of the load line is what? Cut off. That's when there's no current going through the transistor, all right? So you're going to get 15 volts. So that's the two ends of the load line. So here's cutoff, 15 volts, and there's the half amp for IC sat. Okay. VCE is going to be 15 volts when this transistor is completely open. Think of it as a paper clip. You put a paper clip across here, measure the voltage across the paper clip, 0 volts. So 15, you're going to measure on your meter right here. At the emitter, at the load, you're going to get 15 volts, right? When this is, no, you're not right here. You're going to measure 15 volts across the collector and emitter when this is open, when there is no paper clip in there, okay? So when you put the paper clip in, you get a short, so you get 0 volts on VCE, but you get full current going through the circuit, all right? Pull the paper clip out, that's cut off. All right, so now you get full 15 volts across here, no current flowing. And in practical operation, you're never going to get full output voltage. You're not ever going to be able to get all the way up to 15 volts, okay? Because there is some bias currents required. So it's always going to be a little bit on. And that makes it so that the Class AB amplifier, such as this one, is not ever 100% efficient. There's always going to be some power dissipation going on, of course. You can always make it better by using Darlingtons and things like that, which we talked about. It doesn't have any voltage gain, right? Why? Recognize this. Remember, the load is coming off of the emitters. That's a common collector setup. Common emitter. Common emitter never has any voltage gain, but it has power gain. Lots of power gain, no voltage gain. And that's what I just said. Common collector amplifiers. Emitter follower, I should say, not common emitter. Okay, so now we're putting Darlington transistors in here. That's going to help because you're going to have more current gain, right? But you have to double up the diodes. Why? Because you now have 0.7 and another 0.7. So you have 1.4 volts here, 1.4 volts here. Diodes are cheap, no big deal, all right? But you get a lot more current gain. And that's why 4 diodes are used, because of the 2 base emitter drops on the common collector or emitter follower amplifiers. So if you don't have matched diodes and transistors, what do? Well, you can kind of put in this little bias tweaker circuit here, which is kind of cool. It actually replaces one of the resistors in the circuit, one of the diode dropping resistors, with this little transistor, which is adjusted, the bias of which is adjusted with this potentiometer. Okay, so here we have a voltage divider bias on this this transistor. So this transistor is turned on slightly or off slightly depending on the setting of this potentiometer, and that's going to replace that resistor that used to be another 10K down here, maybe. So it's not going to be 10K anymore. It's going to be something other than 10K, maybe 10.5K or maybe 9.5K or something. In order to compensate for the differences in these bias voltages. What's the problem with this, though? This transistor Q3 is going to maybe, depending on currents, it could get a little warm because it's always on. Okay. Whereas these transistors ideally are not always on. They're only on for half cycle. Yeah, so you adjust this for 0 volts, adjust R5 for 0 volts, and that way you know that you have an equal amount of bias voltage on each one of these transistors. And you could build this and it would work fine. There's a 3904, 3906, 3904. This is a very prototype buildable circuit. It would work great. Okay, let's talk about Class C amplifiers. So we did Class B, we did Class A, Class B, Class AB. Now we're going to do Class C. So Class C amplifiers are in a category called nonlinear amplifiers. They do not produce an output waveform that represents the input waveform. And is that important all the time? No, it isn't, because sometimes all you want is a frequency. And if you can match the frequency on the output with the frequency of the input, well, you've accomplished that. And that's what Class C amplifiers are used for. They're used in RF applications for oscillators and modulators and things like that. Now, the advantage is that they're super efficient, okay? If you look at this circuit here, this is a bias. A bias is it off. This transistor is off all the time, except for when Vin exceeds this VBB voltage plus 0.7 volts. It just turns it on a little bit. So usually this is biased so that, for Class C, it's always the way, so that the transistor only conducts at the peaks of the input waveform. So it turns it on briefly. pops it, just switches it. And so this transistor is off most of the time. And then it's on only for a small percentage of the input waveform. So it just turns on briefly, boom. And when it turns on all the way. So what's the power dissipation of a transistor when it's off? Well, it's zero, right? Because there's no current going through it. There's no power. Power is current times voltage. Well, if current is zero, you have zero power, okay? So that's when the transistor is off. So here comes the input waveform. It gets towards its peak, turns the transistor on just briefly, all the way on. So when you turn the transistor all the way and it goes into saturation, VCE is zero. You have 0 volts, but you have full current. So 0 volts, again, times full current. You still have 0 power. So this transistor is living a pretty good life. It's not getting hot. And so that's why Class C, this Class C topology is used in RF applications to create frequencies, high power frequencies. These are, we're talking transmitters. Okay, so you hook this V out up to an antenna, for example. You're on the air, okay, with a frequency. And you can modulate this a little bit. We're going to put a little filter in there. And this is what I was talking about here. They're very efficient. So we put a little filter on here, a little tank circuit. And lo and behold, what happens with the tank circuit is if you put a sine wave in here that only conducts this transistor at the very peaks, what happens is that tank circuit filters out all the other nonlinearities, and whoa, out comes your sine wave. So we fixed it. We made it so that the output does represent the input. Now, you have to be careful because this is a resonant circuit. It's tuned, right? That means it only really works at one frequency or a very narrow range of frequencies. So its spectrum is very narrow. So generally speaking, we're a fixed frequency situation here. If you vary this frequency, your output waveform is going to drop in amplitude greatly. Transistor's still going to try to conduct, but you're not going to get much out of it because this tank circuit's going to filter it all out, okay? Now, there is some bandwidth to this tank circuit. There's some. So you can do FM, frequency modulation, over a very small modulation index, but you can do it. So here's a good graph showing that the current in the collector is just bleeping on just a little bit at the very peak. See at the little peaks? All right. So as you turn on the V out, okay, as you conduct V out, it's only on just a little bit. And here is showing it on the input. VP Q conducts only at the peaks, just at the peaks. And we have a capacitor resistor arrangement here forming a little high pass filter. So again, you only conduct at the peaks. And this is clamper bias, called clamping bias, where you clamp it down, clamp the transistor off. So it only conducts at these peaks at 0.7 volts. Very common circuit, okay? And you'll see this if you examine schematics in your career and so on. You should be able to recognize this, as you should be able to recognize the other circuits that we've covered. But this is pretty distinguishable by this tank circuit up here. Real common, okay? It's particularly in RF circuits or oscillators. Okay, here's a nifty little troubleshooting circuit exercise. So you just built this on your Valencia proto board, and you assume all the parts, you foolishly assume all the parts are good, if I can say that, and you find there's a problem. It's only conducting at the negative half. You go, oh, darn it. So you call me or one of the lab assistant over and say, what's wrong with my circuit? So we say, well, here, try some of this stuff. Check some voltages. Check that first, right? Well, I got my 15 volts. Minus 15 volts. Yeah, got it. You better check your ground too, although I don't think that's checked here. Well, there's 0 volts at the input. That's without a signal. That better be 0 volts. Minus 3 volts? I don't think so, right? Because D2 is a diode. So this is 0 volts going down through the diode to the cathode. You should get, what, minus 0.7 volts sitting here in order to bias Q2 on, or almost on. So that's the problem, is D2 is a bad diode, okay? Now, the other thing I would check on this, okay, is always check your ground. So a lot of times it's a ground problem for these circuits. It's funny how that works. Okay, here's a couple of key terms. Type of amplifier that operates entirely in its linear active region is class A. So they're very inefficient. The Q is right in the middle of the load line, and so it's on all the time. Power gain is output power divided by input power. A couple of formulas for that. Again, I will emphasize again, you should make a formula sheet for the next exam, which is in early November. Efficiency, ratio of the signal power divided by the delivered to the load to the power from the power supply. So again, how much power do you have to give the circuit in order to create an output power through the load? All right. Now for class A, that's going to be a lot more power you're going to need to give to the circuit in order to deliver something to the load, whereas class AB, class B, or class AB, not so much. Interestingly enough, class B, it operates only in 180 degrees of the input socket because it's biased at cutoff. We don't use class B that much. We use class AB with those diodes in there in order to get rid of what? To get rid of the crossover distortion. Okay? All right, so I'll talk to you next time. If you have any questions, please post them in the discussion area on our Canvas site. Thank you.